Okay, so this is my example of how to do take a polynomial, break it down into its linear factors, and then to expand it to check. So the polynomial I decided to choose was this one. It's a 4th degree polynomial. So the first thing I probably want to decide on is how many possible real solutions could there be. So looking by applying Descartes' rule of signs, I noticed that there are 3 sign changes where it changes from a positive to a negative. The coefficients change from a positive to negative. So there are 3 sign changes. So that tells me there could be 3 positive real roots, or there could be 1 positive real root. Then to test the negative zeros, so I substituted in negative x into my polynomial, and I noticed how it changed the signs, and what happened was there was only 1 sign change. So that tells me there could be, or there has to be, 1 real negative root. There could be 3 positive real roots, because that was one of my results from the first time, and that does add to 4 zeros, which is what the fundamental theorem of algebra tells us, that take a look at the biggest degree, and that's how many zeros there'll be. So there could be this. Now the other option is we know there's still going to be 1 real root, but the number of positive roots could decrease by 2, so that means there could be 1 real positive root, and then there would have to be 2 imaginary or complex roots, and that adds to 4 also. So those are the possible values I could find. So now comes, what could I possibly use for roots? So the one thing, the p number is the 195, so I had to list all the factors of 195. So I broke it down. I knew it was divisible by 3 because the sum of those was 15. The sum of the digits was 15, and then I just broke it down, and then 65 is 5 times 13. So what are the possible combinations of numbers I could multiply to get 195? Well, I could do 1 times 195. I could do 3 times 65. I could do 15 times 13. I could do 5 times 39, and that's all the possible factors for the 195. So then I used the rational root theorem to list my possible roots, and there's all my factors of 195, and here are all my factors of 20, which is the leading coefficient, and those are the possible roots. And now I've got to decide what to use. Is 195 going to be a possibility, or is 195 over 20, or is 65 over 20 going to be a solution, or is 1 going to be a solution? So we're going to use this lower bound test to decide. So I decided to pick an easy number like -1, and I ran my synthetic division on it, and notice what happens with that last line. It's changing from a positive to a negative, negative to a positive, so it's alternating positive and negative. So that tells me that -1 is indeed a lower bound. I do not have to test any numbers further smaller than -1. So how about an upper bound? Well, I thought I'd try 39 and see how that worked out. Well, I ran the synthetic division on 39, and notice how these are all positive. So since that's a positive number and these are all positive, 39 is an upper bound. I know I won't find 39 is not a 0 because it's not, the remainder's not 0. And we know that 39, there's no numbers larger than 39 that are roots. So then I decided to start finding my roots. Well, I know there's supposed to be 1 negative root, so I decided to try, and I knew -1 was a lower bound and not a 0, so I decided to try -3/5 since that was the next number closest to 0. And lo and behold, it worked out that the remainder was 0 with the synthetic division. So -3/5 is a place where the graph crosses the x-axis. It is a 0. So to write that as a factor, I subtracted. I wrote x equals -3/5, brought it over as factor, and then I didn't want to deal with a 3 over 5, so I multiplied by 5. Remember, this is equal to 0, so it's legal to multiply both sides by 5. And then I've got that last line of my synthetic division, and remember our discussion earlier how when you do synthetic division with a fraction, like 3/5, that denominator is an extra multiple that occurs. So what I did is I divided each of those numbers by 5, and then I rewrote my polynomial. Remember, the power decreases by 1 because I divided by that x equals negative 3/5, so that reduced the power by 1 and left that. So now I know I've got the one negative root. I'm going to try a positive root, and since 39 was an upper bound, 5 is the next number down, so I decided to run synthetic division with 5, and that had a remainder of 0, and so that left me with the first 0 as a linear factor, the second 0 as a linear factor, and then here's this quadratic factor that's the result from that last line of the synthetic division. So then I decided to see if I could possibly factor 4x squared minus 12x plus 13. So I decided to apply the discriminant, the b squared minus 4ac, part of the quadratic formula, and notice that worked out to be negative. So that tells me I do have imaginary roots, or two complex roots, and that confirms what René Descartes' rule of signs told us, that there would be one negative root. There could be 3 positive roots. We found one positive root, and then there's going to be 2 negative roots, obviously, or 2 imaginary roots here. So because I need to have an imaginary root, I've got to use the quadratic formula, and I've already done the 4 b squared minus 4ac with a negative 64, so that the square root of negative 64 is 8i, we write it as. And then, of course, I want to break that out to get my 2 solutions. So I broke it out to 12 over I plus 8 over I, 8i over 8, which gave me 3 over 2, because I divided both of those by 4. 3 over 2 plus I, and the same thing for the negative one, and that we know that complex roots come in conjugate pairs because of this. So there's my 2 other zeros. And to write those other zeros as linear factors, I just solved this equation for 0. I brought it over so it's equal to 0. There's the first factor, there's the second factor, and then to list all the linear factors, there's the 2 reals, and here's the 2 complex, 2 imaginaries, and then I decided to distribute the negative through just to clean that up a little bit. So there's that polynomial broken down into its linear factors. So now I have to expand this all back out to make sure I did this right. So here I'm decided to tackle the complex number parts first. So I'm going to have to FOIL that. So the first thing I did was to multiply x, the first x times the second polynomial. That gave me that. Then I decided to multiply the negative 3 over 2 by the second polynomial, and that gave me that. Using the distributive property, gave me those numbers. And then, of course, I've got to multiply the the negative I through. And now to put all that multiplication together so I can combine like terms, I wrote each result on a separate line. And then if I add those up, I'm going to get x squared minus 3x plus 9 over 4. And then the negative, the I squared, the negative I squared, remember I squared is negative 1, and negative 1 is positive 1, so 9 fourths plus 4 fourths is going to be 13 over 4. And then that, I didn't want to have to deal with the 13 over 4, so then I remembered, hey, I am setting this equal to 0, so I can multiply, clear the 4 by multiplying everything by 4, which makes it a much easier trinomial to have to deal with. Now I've got to expand out the 2 real solutions and 2 real roots, and that gave me that trinomial. And now I got to multiply the 2 trinomials together And so the first thing I did was just multiply the 5x squared times everything in the second trinomial. It gave me that. And then I had to multiply the negative 22x by everything in the second polynomial. And I multiplied the negative 15 by everything in the second polynomial. And then to combine all those terms together, I just wrote each result on a separate line, combined like terms, and I got my original polynomial, so it's no longer fractured. And that's what we do to solve this.